you. Hello, hello everyone. My presentation will provide an overview of the work carried out this fiscal year as part of a project on aquifer and groundwater characterization in the lower Grand River Watershed in southern Ontario. This project was launched in 2024 in response to a request by the director of the Environmental Committee at the time of the Six Nations community to the federal government for assistance in addressing the poor quality of groundwater in the reserve. Today, I will mostly focus on our field campaign conducted last fall. This project involves many great people from the federal government, from 3 GSC divisions, from ECCC, from 3 provincial ministries, and in particular ODS, 4 universities, 2 consulting firms, and 1 member of the Six Nations community and her postdoc, who are both affiliated with a university and Six Nations Polytechnique. And we have the pleasure of having 2 PhD students. The study area corresponds to the lower part of the Grand River watershed, so about 2,000 square kilometers, with 2 First Nations reserves located in the middle, Six Nations, which is the largest in Canada, and Mississaugas of the Credit, which is just next to it. As you all probably know, this region in general is mostly rural and quite populated. We decided to select a much larger study area than the 2 First Nations reserves in order to properly understand the context and the different water quality issues, which include those related to agriculture, road salting, and hydrocarbon development, because there are many old oil and gas wells that were abandoned with the methods used at the time. So all these issues pose serious problems because some parts of the aquifers are brackish, gas-rich, or contain other compounds, making sometimes groundwater unfit for consumption. In particular, H2S, a toxic gas, represents a major health issue because as methane escapes from deep hydrocarbon reservoirs and migrates to the surface, it can pass through evaporite layers and then eventually forming H2S. One of our field crew members became sick during the sampling campaign due to H2S exposure. The shallow bedrock in the study area mostly consists of the Salina group, shown in yellow here, that covers most of the southern half of the study area. This group is mainly composed of course, evaporites, but also dolostone and mudstone. And to the north, in beige, there's the Guelph Formation that is mainly composed of dolostone. The superficial sediment units in the study area are mostly fine grained, so they well protect groundwater against surface contamination, but they do not favor infiltration. So that brings me to the hydrogeological context. So again, as you probably know, this region contains a lot of wells, but a lot of people struggle with their water supply, especially in the southern half of the study area. Because both quantity and quality can be poor. Many residents have wells completed at the interface between superficial sediments and bedrock because there's some water there. Some people use their wells simply as a cistern that they have to regularly fill with water trucks. And some people buy water jugs for cooking and drinking due to the poor water quality. Some farms need to use ditches and ponds to collect rainwater and snow melt because the yield of their well is insufficient. So as mentioned before, due to geology and also the different activities in the area, groundwater may contain, to varying degrees and depending on the location, sulfate, sodium chloride, nitrates, methane, and H2S, hydrogen sulfide, because there are many legacy oil and gas wells in this area. So based on these issues, the objectives of this project are first to understand groundwater flow in the study area, This involves characterizing the properties of the shallow aquifers and assessing recharge and discharge areas and rates, and integrating the knowledge gained in 2D and 3D coupled numerical models, including predictive models, notably for climate change scenarios. And the second objective is to study the impact of natural and anthropogenic contaminants on the region's water resources, and this involves characterizing the quality of surface water and groundwater, and using air and soil gases to better understand and potentially predict contaminant sources. And also explaining the occurrence of specific compounds or isotopic values in specific areas. As part of this second objective, a study of the history of the landscape and environmental changes over the past few decades and the impact on culture, health, and quality of life is being conducted based on interviews and discussions with members of the two Six Nations communities. And this study is being supervised by a member of the Six Nations community who is also a professor at McMaster University, an emeritus professor. Hafsa's PhD project is closely linked to the first project objective. It aims to characterize properties of the different geological units and quantify both recharge and discharge. In order to assess discharge to streams, she already performed a lot of fieldwork, as you can see on the photos, involving a thermal camera survey with a drone last week. Later, she will develop a conceptual model and later again, numerical models to investigate surface water and groundwater investigations using hydrogeosphere. Hafsa will talk about her project on a Thursday afternoon. Julia's project, PhD project, is closely linked to the second project objective as it focuses on the assessment of groundwater quality by investigating geochemical interactions between surface water, groundwater, soil gas, and atmospheric emissions. Julia began last September, and she participated in the first sampling campaign. This fiscal year, we installed 12 monitoring wells in 7 sites that are identified using red stars. They are all located in the southern half of the study area. 6 monitoring wells were drilled last fall, and Abigail Bird, that you all know, had to go back in January to supervise the last 6 ones because everything did not exactly go according to plan for a variety of reasons. The selection of sites were mostly based on geological and geochemical interests. We wanted to have a good spatial distribution, and of course we had budget constraints, so we wanted to find locations where the Guelph Formation was not too deep below the Salina Group. So we began drilling at this site, site number 1, in what we call Stu's Corridor, because Stu Hamilton, that again you all know, discovered that in this specific area, some wells had anomalous sulfur isotopic values of sulfate. Denis Lavoie, who will give a presentation right after me, will present his preliminary observations on faults in this specific area. We then moved on to site number 2, which is very close to the reserve, and we were rapidly notified that this area was the subject of real estate disputes in 2014 and 2020. So we realized it wasn't a great idea to drill there, but we were authorized to drill the wells and we sampled them right after. But we told the Office of the Elected Chief of the Six Nations community that we would not go back to this site unless we were invited by the community. And we decided to relocate the 2 sites in green because they were also very close to the reserve and thus on contested land. So we had to stop drilling at the end of October after drilling at sites number 3 and 4 because we needed time to obtain the drilling permits and to sign agreements with the counties. So this is the reason why Abigail had to go back this winter to supervise the drilling of at the last 3 sites. And as a result, more than half of our monitoring wells are located outside the Haldimand Tract or corresponding to contested land. Field work conducted last fall included, in addition to core drilling, work related to these monitoring wells, such as quaternary sediment and rock sampling, borehole geophysical logging, slug tests, and of course the installation of pressure transducers. Field work also included Guelph permeameter tests, soil gas measurements, a thermal camera survey and a magnetometer survey, both using drones that took place last week. And finally, groundwater sampling, which I will talk about in the following slides. We sample our monitoring wells and 2 residential wells. For the moment, we have only received results for general geochemistry and dissolved gas measurements, but it is enough to confirm that groundwater quality is generally poor for different reasons, including a high TDS content. TDS is often above 1,000 milligrams per liter, so corresponding to brackish water in bedrock wells. And also due to the presence of nitrates, methane, ethane, and propane, and H2S in varying concentrations. But still, water is often very bubbly and smelly. Groundwater is either of the calcium sulfate type, which is not very surprising since most of our wells are drilled into the Salina group, and that contains a lot of evaporite layers, or of the calcium bicarbonate type in superficial sediment wells. Because we haven't received a lot of lab results yet, I will present some general information about the 7 sampled wells themselves. So this is a schematic of site number 1 in Stew's Corridor. We drilled twin wells, meaning that we drilled 2 wells very close by, but at different depths. One of them is screened at the bedrock interface, and the other one is drilled deeper into bedrock with an open section. So the bedrock well is about 125 meters deep, and we sampled it at 4 depths. Water is of the calcium sulfate type, and the concentrations are really, moderately are high, and they are very similar regardless of the depth, likely because the high TDS content that is above 3,000 milligrams per liter results in a higher density than fresh water, so groundwater tends to sink at the bottom. The shallower well is of the calcium bicarbonate type. It has moderately high values of TDS and sulfate, and the nitrate concentration was way above the drinking water limit. Site number 2 is another site with twin wells. The shallower well ended up being dry, although there was water at the end of drilling, and the provincial database shows that the static water level in this area should be between 8 and 12 meters. But 2025 was especially dry, so we will probably be able to sample it this spring or even this summer. The bedrock well was drilled down to about 76 meters, and we sampled it at 3 depths. The concentration, the water type and concentrations are very similar to site number 1. Fun fact, when we arrived and we used a manual level, the manual water level probe, we lowered it and we rolled it back up, and I had a little moment of panic because its tape was covered with a black film. So we tried to extract this black substance as best we could and put it in distilled water, and Laura sent it to the OGS lab. That told us after a few weeks that it was magnetite. And I talked to Stu Hamilton a long time after that, and he told me, oh, it's just iron sulfide because you have sulfur in your groundwater that reacts with the metal casing. He was not surprised at all, but I was, because I had never seen that in my life. This water was extremely bubbly and very smelly, as you can imagine. At site number 3, we drilled down to 50 meters, but we screened it in a very nice permeable sand layer. So this way we were able to have 50 meters of core, but we are able to sample water that is representative of what people drink in this area. At site number 4, we drilled down to about 32 meters, and this well was screened at the bedrock interface. These wells have water type and concentrations that are very typical of their respective type. The 2 residential wells that were sampled, according to the water level records, they should be both into superficial sediments, but residential well number 1 has values that are very typical of a bedrock well, or at least at the interface. But this well was drilled in 1975 and is buried, so we'll never be able to investigate. Residential well number 2 is much more recent and has values typical of a superficial sediment well. The nitrate concentration was a little above drinking water level. Just to finish, we're at the stage of preparing maps and graphs as we receive the results. As you can see on these maps, most of the data come from the OGS database, and we are adding the few data that we have, and we will continue to have more because we are supposed to drill again next fiscal year. Thank you.